Welcome to another video. Today we're going to be doing a walkthrough a system design interview problem. I've actually seen this asked at big tech companies. Most recently I saw this asked at Amazon, and it's design a contest voting infrastructure. Actually, let's look at the problem statement. So we need to design a leaderboard for a multi-round contest, something like American Idol, but just think of any contest where there's a bunch of contestants and audience members vote after each round, and the contestant with the least votes gets eliminated. So clearly the winner is the last person standing. Now that we have the problem statement, we still don't have enough information to actually start doing the design. So you shouldn't be jumping to doing a design at this stage. We need to do some requirements gathering. For requirements gathering, what you're looking to do is compile your functional requirements and non-functional requirements. And as part of that process, you would likely need to clarify 1 or 2 points, maybe more, with the interviewer, so you can actually have a good understanding, so you can state your assumptions and the interviewer can object or confirm if your assumptions are true. So what I'd like you to do, even if you're a beginner, just try and think about what kind of questions you can ask at this stage. And obviously this question should help you with solving the problem. So think about what you're kind of gonna need to solve this problem. Start thinking about what you might be doing, and those should kind of inspire questions. So do spend some time, maybe pause video, think about the kind of questions, and then we'll move on. A good first question to ask would be something to give you an understanding of who the users are in terms of the quantity, so how many users and how they use the system. So is there a period where they use the system more than others? So in the context of this problem where there's voting, is there a voting window? You want to understand what peak usage looks like. This is a kind of good starter question to ask. Just to make a quick point on stating your assumptions so the interviewer can object or confirm. In this particular problem, one common assumption candidates make is that each user has one vote, per contestant per round. But it's always good to state that and say, is it safe to assume that? And the interviewer can object or confirm. In this case, actually, each contestant has 3 votes per contestant in each round. So this may or may not be relevant in the context of your design, but if you're at some point going to go into a deep dive into how you're storing votes, for example, or deciding if people have exceeded their voting limit, if it was 1 vote per contestant, maybe you'll be using some kind of Boolean, saying, have they exceeded the votes or not, true or false. But if it's 3 votes, maybe you might actually want to count and use integers and track how many votes the user has placed so far. But the whole point of this is just state your assumptions so the interviewer can object. It'll save you from a lot of hassle, because what tends to happen is you have some implicit assumption, you kick off with the design, and at the point where you're applying your assumption or not applying it, it becomes apparent. But so much time has passed and you might not have enough time to recover, and the interviewer is not obliged to let you know. So do state your assumptions. There's actually some requirements gathering walkthroughs on the site codectionary.com. So if you actually go there, you can scroll through a few and in the system design course and have a look, but you can do that after the video. So let's move on. So if you ask the right questions, you should have come up with functional requirements that look like this. So we understand, if you look at the first two, just talking about the fact that the user should be able to place votes, and we're pointing out that the user can place up to 3 votes. So the limit is 3, not 1 per round, which could be useful when we do deep dives. But for the high level design, we just understand that users can vote, and we're told users can distribute the votes how they want. So all 3 votes to the same contestant, or they can spread it across different contestants. Cool to know. Maybe that's relevant when we do a deep dive, or make some data structure choices or whatever. Another important question that will be useful to ask, okay, yes, users can place votes, but can they actually see the votes? So a good question to ask as a candidate would be, do the users need a leaderboard or some kind of view where they can see the current standings? And the interviewers confirm yes. And you can then clarify, how real time should this be? To the millisecond? Is a 5-minute lag tolerable, and so on? In this case, we can assume, some 5-minute lag is tolerable, but that's something you clarify with the interviewer. We know that the contestant with the least votes gets eliminated. Maybe we don't use that in the system design, but something to point out, because maybe does the system need to do anything to eliminate the contestant, or is this something we just need to display in the front end view that's, tags users eliminated? In terms of non-functional requirements, if we ask the right questions, is there a voting window? Like, how are users using the system? What kind of users do we have? What's peak usage look like? We can get this kind of understanding that there's a 24-hour voting window, which the interviewer can confirm. And you as a candidate will recognize during that voting window, you want the system to be continuously available. I have 99.9% availability here, but could be 99.99. The point is, system should be continuously available during that voting window. Outside the voting window, it doesn't really matter that candidates can't vote. Users, audience members can't vote because it's outside the voting window. So maybe that period is good for any maintenance upgrades. But during that window, it will make sense that users can actually view the leaderboard. But I think the voting window is the critical period. In terms of usage, this is not really something you'd necessarily be able to estimate. You could propose some numbers, but this is something that ideally you want the interviewer to provide. Like for the contest, we're told, okay, there's 50 million votes in a 24-hour window, and a peak voting, it's 1 million concurrent users voting. And another important question would be about like security, just in terms of preventing abuse and fraudulent voting. So that's something you should propose. Even though you don't get time to actually work on this part, you can at least flag it as something as important. Should interview that you're thinking about how the system will actually work in production, but because of interview time constraints, you might not get a chance to get to the section. So I have quite a lot of things so far. Maybe you have other requirements you would have pointed out, but at this stage, this is enough information to actually do a design. One thing I always recommend is, once you've gathered all the requirements, and you should probably have something that looks like this in your whiteboard. You have your functional requirements, your non-functional requirements listed out, and you literally get the interviewer to agree, like a contract. Like, does this capture what you want me to design? And for your non-functional, you can have classifications on the key things like scalability, performance, availability, and these kind of things would help you ask the right questions. You'll also notice I have this must do, could do tags, and that's something that's useful to have from a perspective of prioritizing what's important, because you're time constrained in interviews and you can agree with this priority with the interviewer. I have some potential problems to deep dive, which I'll come to, but this is more of like a template you can have of what your whiteboard might look like at this stage. So when you have your requirements compiled and kind of agreed with the interviewer, or even prior to doing that, one thing you can also do before you start, designing, is you can start thinking about the potential problems that you might want to solve. If any come to mind, you can just note them down. So in my case, everything here is pretty much the same, except on the consistency side, because I just had this categorization, it prompted me to think of, what data I'm storing and what the consistency model I might use would be. And I was just thinking from a votes perspective for the leaderboard, if I'm a user and I'm looking at the leaderboard, let's hone in on one contestant. Let's say they have 1 million votes. And if I do a refresh, or in the next, couple of minutes, I check that contestant votes and I see they have 500,000 votes. There's been a drop. That suggests, they're seeing stale votes, and that's something we don't want to happen. So users should be seeing votes progressing in time, or at least they should see the last value they saw. They shouldn't be going backwards in time in terms of the votes, because there's not like negative voting. So on consistency, I've noted that I want to have at least monotonic reads. So read after read consistency, if you want to call it that. And the idea is that everything I just described. So if I read that the user has 1 million votes, I shouldn't then see the user has 500,000 votes because I ended up reading from some, database node with stale data. That definitely shouldn't happen. So in terms of potential problems I can think of at this stage, this staleness of reads that I've just said, ensure monotonic reads. Obviously, audience members are voting. We shouldn't lose vote. There shouldn't be data loss. So data loss prevention is very important, especially with regards to votes. I have limited votes. We noted that users can not vote more than 3 times, so there's a limit. It's just, again, a potential problem, but something to note down when I'm doing my design or deep dive. And then we have atomic vote updates And that's in the context of concurrency, and just the idea that we have contestants, and there could be multiple people voting for a specific contestant, at the same time. And as we're doing these updates to the vote, we should make sure they are done atomically. If you're not familiar with like concurrency, this might not make so much sense to you, but the idea is, if I was put it simply, if a user has, let's say, 50 votes, and there's 2 votes coming in to increase the contestants' votes by 1. Once those 2 votes are processed, we should expect to see that the vote has gone from 50 to 50 plus 2, so 52. But if some concurrency race condition issues happen, we can end up with a situation where maybe the user just has 51 votes, which is problematic. So we're not going to dive into that right now, but that's something that is very important, that we're actually counting the votes properly. So we don't lose votes, we count the votes, we capture all the votes, we respect any limits on votes, and we make sure that when audience members are viewing the votes, they are viewing them in a monotonic fashion. It doesn't have to be real time, but at least in this problem, based on our clarification with our interviewer, which I've noted here, so we should be able to have counted votes within 5 minutes of the vote closing window. So we tolerate a 5-minute lag in terms of accumulating votes. In your interview, you had like a similar problem. The interviewer might be, I want something really real time to the millisecond, every minute, every second, whatever. But in this case, it's 5 minutes, which is a more relaxed constraint, which makes our life easier. Now we're ready for a high-level design. And at this stage, it makes sense to try to get like an intuitive feel for the problem before you start, with the design proper. And by that, I mean, like intuitively, just putting the formal requirements and non-functional requirements aside. Like, what do we actually need? So we need a place to store the votes. It could be a database, it could be a cache. But we definitely know we need a persistent store so that for data durability. We don't know if we need a cache or not at this stage. We don't have to decide yet, but those are things to keep in mind. We need a way to fetch the votes. Of course, if we're storing the votes, we should be able to fetch the votes from the store. So we know there's going to be some reading of data. We know there's going to be some writing of data. And you can ask yourself, is this system more read-oriented or write-oriented? At this stage, you might have more questions for the interviewer. I would say we have a voting window, which is with the primary purpose is really for voting. And at all points in time, users can read. So I'll say during the voting window, we definitely should prioritize capturing these votes. So we'll prioritize writes there. Outside the voting window, reads prevail. So keep that in mind in terms of your design choices. We definitely want to handle peak load. So we want the system to be scalable in this regard. We want no data loss. So, that ties into the storing the votes, but we need to store them in a way where there's no data loss. And I've put a note where in the context of even the data centers or availability zones, if there's like the physical data centers, there's a flood or power failure or act of terrorism or something, we still don't want data loss. So we definitely want to have multiple data centers involved, multiple availability zones. We talked about not having stale reads, and we talked about, users not being able to exceed their voting limit. So we kind of had an intuitive feel for kind of what we're trying to achieve. Let's go ahead with the design. So let's put the pieces of the puzzle together, the components that we know for sure are going to be important. So we can start with the client or the user. So these are people that are placing votes or fetching votes, to see the leaderboard, that's standard stuff. And I have a bunch of load balancers here, a global load balancer. So at this stage, you can clarify with the interviewer if the audience base are distributed, across multiple geographies, multiple countries. This is also something you could have asked at the requirements gathering stage, but you might not remember to do that. But although this is quite standard, maybe something you should always ask, who are the users, how they're using it, how they distribute it globally. These are like your standard questions you're going to ask in most problems. And then I have a local load balancer. So the global load balancer will distribute votes to the nearest sort of data center based on latency and other factors. And we have a local load balancer. So when a request to place a vote or view a vote hits a certain data center or availability zone, it will then distribute those requests to the infrastructure within that data center. You'll notice I have here labeled data center 1 of n to indicate that I'm going to have multiple data centers. So n is going to be greater than 1. You can say that to the interviewer. for us in this problem, it's important that we have continuous availability during the voting window. So we can't afford to have just one data center. What if something goes wrong there? It's very rare to have a situation where you just have a single data center. I don't want to say, but I'll be surprised to see many situations where having one data center is fine. That means you must be able to tolerate the data center going down. So that means what you're doing is probably not important, which is fine. So moving on, behind the load balancer, I have an API gateway, and that's just when requests come in. This is the centralized entry point, and this gateway will, process this request and distribute them to the right, destination. I have a queue here because we know that during peak usage, we might have 1 million concurrent users voting. The queue will help to level the load during peak times, especially have 1 million concurrent votes coming in. For example, it's very easy to think of an idea which you don't have to commit to, but a request to place a vote comes in, we dump that in the queue, asynchronously acknowledge the vote and respond very quickly. So that's a very easy to handle request. And then we have some services. Definitely there's going to be one that's going to process that vote and pretty much count it. We haven't decided how we're going to consume the votes, but I can imagine aggregating votes or consuming votes in bulk, assessing the different contestants, saying, hey, contestant A has 100 votes, so plus 100. Contestant B has plus 50 votes, so accumulate them and then do that update in bulk. Essentially that would help with throughput. We might decide to have other services for different concerns, so maybe a separate service for counting the votes, a separate service for fetching the leaderboard. We might decide to have the separation of concerns. We know that ultimately the votes need to be stored because we don't want to have any loss of votes. So we need a persistent layer storing these votes on some kind of disk. But what if this data center goes down? Does that mean we've lost the votes or we don't have access to the votes? There'll be some kind of inter-data center replication, so that even if data center, the primary one, goes down, we can resume counting and fetching from the other data center. So this is the pieces of the puzzle. We're making progress, and now it's just a case of diving a bit deeper, connecting pieces of infrastructure and making more decisions, like how many queues do I actually need? I put I here just to indicate this is a generic queue, but I may decide to have more queues. I might decide to have partitions we will get to in the queues. So we need to make a few more decisions, but we're getting close. We have a picture. Do I need a cache or not? Or am I just okay with having a database? If it's just a database, which one? So how are we splitting the services, and so on and so forth. So let's dive a bit deeper. Now that we have rough idea of what our architecture is going to look like, let's dive a bit deeper and finalize our design. So we've already spoken about how we have users who could place votes or fetch votes. So let's think of a user placing a vote. The sender request, it goes to a load balancer, which does some latency or geography based distribution, also factoring in the health of the downstream services in terms of the endpoint it distributes to. We have local load balancers in our data centers, which then distribute load across multiple instances of my API gateway. So I've decided to have an API gateway, which is going to be a HTTP server. So I've decided to go for a RESTful endpoint. This is not so much of the important part of this design, so I don't want to dive into it. So I'll let the interviewer know that I'll come back to it if they're interested. And essentially it's a centralized entry point, and it's going to have multiple instances. So it could be like a multi-process HTTP server. I could even have something like Flask, or I could do something better that's better for throughput, like Fast API. I'll have multiple instances. They'll all be stateless, and this gateway is just a central point. It has multiple endpoints for collecting votes. Users can use it to register. Users can use it to request the leaderboard. It would also help with authentication, and I've decided to go with a managed authentication service. So the request comes in, we're going to say, okay, is this person who they say they are, and are they known to us, kind of thing. So we can use a managed authentication service like Firebase or something else. This is not the most interesting part of this design, so I don't want to dive deep into that. It also performs some rate limiting. Our global load balancer can do this. I can let our API gateway do this. We can do maybe some more custom rate limiting if we want. And for votes, we're going to process them asynchronously, because the idea is we could have them coming in, think of fast, we could have millions of votes per second. And I've decided to go for a queue with multiple partitions. So let's think of something like Kafka, which is quite popular. It's very good for high throughput. It can process millions of messages per second. So for each vote, we just dump a message onto one of the partitions. And the value of the multiple partitions is we can have multiple API gateway instances pushing requests or publishing requests to different partitions in parallel. And when a vote is pushed onto the queue, we can respond to the user with an acknowledge response saying we've acknowledged your vote. That doesn't mean we've counted it, but it means we're going to count it. And if we go with something like Kafka, which is quite durable, it stores messages on the disk, we can be sure that at least we're not going to lose that data. So we can go with something like Kafka with multiple partitions. And this is also valuable because it allows for parallel processing. So we can have multiple consumers. I have this vote counting service. I have a dedicated service for counting votes. And so let's say I go with like 4 partitions and let's say 4 instances of this service. These 4 services could be consuming votes from each of these partitions, and they're going to consume them in bulk. So not one vote sort of message at a time. We can consume like 100 or 1,000. This is something we can tune so we can process things faster. So I have a mechanism for collecting the votes, and what the vote counting services will do is it'll talk to our data layer service. I should step back a bit and maybe slow down. So what the vote counting service actually will do is it'll get a collection of votes, a chunk of votes, and in there we can have votes from multiple users. And let's say the aggregation of those votes is such that contestant A is going to have plus 100 votes, contestant B is going to have plus 50 votes, and so on. We have the aggregate updates for each contestant because all we're doing is trying to count votes for contestants, right? But then we also want to make sure users don't exceed their limits. So what the vote counting service could do is first get how much votes each user that is in this collection of votes has made. So how many votes have they made, or how many votes do they have left, whichever one, through our data layer service, which will query our database wherever that's stored, and it'll keep that information. And when it aggregates the votes, it'll keep track of the user that's voting and just make sure before it counts any of their votes that they haven't exceeded the limit. And then once that's done, we'll perform a bulk. So it's a single request, which will say, okay, data layer service, I'd like you to update the votes, contestant A plus 100, contestant B plus 1,000, and so on. So instead of, let's say there was 1,000 votes we were processing, we're not going to send 1,000 requests to the data layer service. That would be inefficient. We can do that in bulk, so we just have one hop instead of 1,000 requests to the same service. So that's a bit more efficient, more parallel, and that will help with processing peak load. So the data layer service, which we're going to come to later, its job is to interact with whatever persistent stores we have, whether it's a cache or a database. It's also going to be used by this other service, which is, I called it the leaderboard fetcher service. We can call it the leaderboard service. Its job is to handle requests. Job is to help users get the latest status of the vote count. So the leaderboard, essentially. Now, there are many ways to solve this. A few options. One is users could poll. So whenever users send requests, they could poll by poll I mean send multiple requests each time they want to see the state of the votes. So that is possible, and with our rate limiting, we can control users to make sure they don't overload our system. So users send a request, what's the leaderboard? API gateway sends a request to leaderboard fetcher service, which talks to the data layer service, which will query the database and return the votes. But I don't want users polling because that's inefficient. I think what we can do is use server sent events. If we think of this leaderboard fetching, this is a one-way communication, really. We can have a situation where a user is on a certain web page of our website, and what that site does is maybe every 5 minutes, well, it doesn't even have to be every 5 minutes, but it can have an SSE connection. It's literally just a HTTP connection, a persistent connection with our backend. And what would happen is this leaderboard service will have essentially a connection with the client indirectly, obviously, because we have the API gateway and load balancers. And what it can do is every 5 minutes, for example, it'll query data layer to query, our persistent stores or wherever we're storing these votes to get the latest state, and it'll push the data containing, the contestants and their current standings, the number of votes they have. It'll push that to all the clients. And this is something we can do for multiple clients. It's quite scalable. Obviously, there's a limit, but for our use cases, definitely something we can do. So we have like 10,000 or a million users on our website on a certain page that has a leaderboard. As long as they're on that page, every 5 minutes they can receive updates to the table, and this 5 minutes value could be tuned. So in summary, the reason I've gone for this server sent event approach is instead of having millions of users querying maybe refreshing the page or something and querying my backend every second or every minute or so, what we can do is just send them updates every 5 minutes, and it's a one-way connection, and this would minimize the load on our resources. And one other thing we can actually do is tune this value. So if, for example, for some reason we just have way more votes that we can handle, and given that the vote counting service depends on the data layer service and the leaderboard fetcher service also does, we can even just increase this time frame where we said, okay, every 10 minutes we send updates, or every 15 or 20, because for us, during our voting window in particular, it's really vote counting that's the most important. So anyway, we kind of have a rough idea of how we're gonna handle a high volume of votes, and we have an idea of how we're gonna handle a large number of users trying to monitor the current standings. For the data layer, I've gone with we have a data layer service, we have a distributed cache, I've gone with Redis, and I've got with Cassandra for my persistent store. And the rationale is as follows. So if we look at write, which is essentially when users place votes, we store those votes in our persistent layer. That's definitely going to be a lot, especially during the voting window. In terms of reads, so that's like fetching the leaderboard, and also maybe during votes where we fetch the current, like how many votes a certain user has, so we make sure they don't exceed the limit. For the main read, which is the leaderboard, we have opted for SS server sent events. So we don't allow the users to poll, and essentially we control how often we do this read. So we had 5 minutes set, but we can tune that and make that even longer based on our needs. So in a way, we control the reads because writes are the most important thing in terms of storing the votes. So I've gone for a database that's optimized for high write throughput based on its underlying storage engine. I don't have to dive into that now. And a few options we have: a Cassandra, we have DynamoDB, but I've gone with Cassandra. I've also gone with an eventual consistency model. So for me, we don't have to write to the database in such a way where we've written to all the nodes, but if we can write to enough nodes, a quorum number of nodes, or quorum writes across both data centers, so that at least we know that the data is safe, and even if one data center goes down, we still have the data in another data center. That works for me, because we also store the votes in the cache. So essentially, when a vote comes in or vote update comes in, we store the votes in a cache and in our database simultaneously. And we only conclude that the write is complete once enough votes, we've written to a quorum number of nodes. So for example, if we had 4 nodes in each data center, it could be that the quorum was 3, for example. So if we've written to 3 nodes here and 3 nodes in the other data center or some other distribution, the key point is we have the data persisted in both data centers. Because of its eventual consistency model, we know that other nodes will have that data in sync with all nodes will be in sync eventually. But the reason why I can get away with that is the reads for votes, actually, when the leaderboard is fetching, would actually be from the cache. So we write to the cache and we write to database, but we read from the cache. So writes are done to a database that's optimized for high write throughput. So the writes are really quick, and the fact that we're using this eventual consistency means we don't have to wait for replication to all the nodes, which helps from a performance perspective in terms of writes, because we don't have to wait for all nodes to have the same states. We can just write to whatever minimal set we define. So we're optimizing for writes, and at the same time, the reads will be quite quick from the cache because it's in memory. So we do this simultaneously, and once we've written to a quorum number of nodes and updated the cache, and we're going to do strong consistency, and you might think that's slow, but because it's in memory, it's still going to be fast. So we can tolerate that, have our votes written very quickly, and ensure durability. So at a high level, that's kind of what writing votes looks like. Fetching votes, we kind of alluded to, is simply a case of reading from the cache. We wouldn't read from the database because it has an eventual consistency model and all nodes might not be up to date, but the cache, we've gone for strong consistency. So whenever you want to read votes, we read them in memory, and that's really quick. So effectively what we've done here was gone for a write-through caching strategy. We write the votes to the cache and write to data store. For my distributed cache, I've decided to go for Redis, and in terms of configuration, strong consistency, so that all the read replicas, so we'll go, so leader follower, so a single master, multiple read replicas, so that reads can be served by any of the read replicas, which is good for scalability and availability, and we never get stale vote. There's other in-memory options like memcache, but Redis definitely does the job, and it also has this flexibility where if you want to store things in an append-only file, it allows you to do that. That's not something we anticipate we need, but in this case, I'll say Redis and memcache for our particular use case are tied, but Redis tends to offer more, so I've decided to go with Redis. For the database, I went for a database optimized for high write throughput. So I went with Cassandra. DynamoDB was also going to be a good option, but I'm happy with Cassandra, and I'm happy with the eventual consistency model, which means when we do a write, we don't have to wait for replication to all nodes, which helps with reducing the latency, improving the performance. For sure, we have multiple nodes, and this leaderless setup, so availability is ticked. And just to step back from a cap theorem perspective, Cassandra optimizes for availability and partition tolerance over consistency. We don't care so much about consistency here because all our reads are from the cache and we have strong consistency there. So we have something that works. We've justified our database choice. We've roughly justified our distributed cache choice based on something that just works. I mean, our use case is quite straightforward, so maybe memcache could have worked, but Redis works as well. So even though we could dive even deeper into other aspects of the design, so for example, maybe justifying the choice of Redis for the in-memory cache, or talk about the API and so on, just because interviews are quite time constrained and we pretty much have something that works in terms of the workflow, now would be a good time to go through the checklist to make sure we satisfy those requirements, so we can make sure if there's any gaps, we can quickly plug it while there's still time. So let's do that. So in terms of the requirements, a user is able to vote up to 3 times per contestant during each voting window. The answer is yes. Can users distribute their votes across multiple contestants? Yes. Does the system track and update vote counts whilst calculating votes? Yes. In terms of scalability, we have Kafka, which helps in that regard. We have multiple instances for each service. We have a load balancer. So all these things help us to scale, and we have options to tune things. We can increase the number of Kafka partitions. When we're collecting votes, we can increase the number of consumers and partitions. We can consume in bulk, which we're doing, but in larger chunks. To help from a performance perspective, in terms of having the votes counted within 5 minutes, that's not something we can easily prove during the course of interview, but something we can tune as we monitor the system when we test it out to make sure that the lag is less than 5 minutes. So for example, by the time the voting window ends, after 5 minutes, we shouldn't still have messages in the queue, that haven't been processed. So we can kind of prove that the consumption rate or the processing rate is such that, the queue lag, or whatever we want to call it, queue depth, they're technical terms for this, but the amount of messages in the queue will be cleared within 5 minutes, then we're good. From an availability perspective, we know we have multiple data centers, we have a lot of redundancy in terms of having multiple instances. If you look at our databases, even Kafka, you can tell there's a lot of redundancy, so I'm not worried about availability. From a consistency perspective, because of what we've done with Kafka, with Redis, where we had strong consistency in terms of the cached state of votes for contestants, we have a situation where users will never have stale reads because all the nodes always have the same data. From a security perspective, we spoke about how users, when they register with their passport, and we'll also do some kind of Face ID and make sure it matches the passport. And that's something we can automate with AI. And we have a managed authentication service. And we also, satisfy whatever the limit is in the number of votes per user. In terms of these potential problems we highlighted, we know that users will not have stale votes. So the votes they see progress in time in the right direction. We don't have loss of votes because before we acknowledge that a write to our persistent store database, our Cassandra database, is done, we make sure that we've written to nodes in both data centers and a minimum number of nodes. So we know that that is already persisted on disk in at least two locations, so we're good. We satisfy limits on number of votes per user. In terms of atomic vote updates, we didn't really talk about this, but in terms of our database, we can always make it clear that when there's multiple writes going on, this can be done with pessimistic or optimistic locking. In this particular use case, because there's a lot of votes happening at the same time, so we have multiple instances of the vote counting service performing write via this data layer service, of which there's also multiple instances. So even though I don't have that here, there's definitely multiple instances. So we can have a situation where there are multiple writes happening, and on the database side, it's very easy to leverage locks. And I would say that in this particular scenario, we should go for pessimistic locking because I think there's a lot of room for contention in that 24-hour window. We can dive deeper at this time. And from a distributed cache perspective, if we have a single leader that we write to and the writes are happening sequentially, then we don't have any concern in terms of atomicity. So just to be a bit clearer on these atomic writes, let's consider a situation where contestant 1 has 100 votes and multiple instances of our data layer service, so our data layer service, which helps to write to our cache and database, are such that maybe there's one that's trying to increase contestant 1's votes by 100, contestant B's votes by 200, and contestant C's votes by 300. What we would like at the end of all these is that contestant 1 no longer has 100 votes, but has 200, 400, 700 votes. That's the end state we expect. And the way the Redis master node would work is it operates sequentially. So it will capture the votes in the order they come. So it increases the votes by 100, then by 200, then by 300. So we don't have to worry about some concurrency issues. So if that's something you're not too familiar with, that's not really a problem here because we went for Redis. One quick correction I'd like to make is to represent the write-through caching properly, because what we have now suggests that cache actually propagates to our service, writes data to the cache, which then propagates to the database. And that's not really what we're going for, although that could work where you can write to the cache and let it propagate to the database, and the write is only acknowledged once both are done. But let's opt for a situation where it's very clear that our service is writing to both the cache and the database, and once both are done, we acknowledge that the write is complete. Before we conclude, I'd just like to let you know that on the Code King site, we have a system design course. It's still in progress, but it has a lot of valuable content, like to help you with requirements gathering, some introductory tutorials. So for example, introduction to in-memory data stores, or this tutorial on database selection in system design interviews. There's some knowledge tests as well to help things that you're learning stick. And we solve some sample interview problems and provide the solutions as well. So you can look at the architecture diagrams and a detailed explanation. So definitely do check that out. There's also other useful content and features on the site. So you can book human in the loop mock interviews with a professional interviewer for any of these domains. We have an AI assistant We can do mock interviews. We can help you when you're solving problems, help you review your code, tell you how you can write more optimal code or write your code in fewer lines, or help you spot bugs. There's diagnostic tests in coding and system design that can quickly test your knowledge, other learning content and advice. And also be sure to check out our Discord community. It's for interview prep optimization. There's over 3,000 members right now. Whatever this is a bit stale. We also organize workshops, which we announce there on the different domains. You can find a study buddy, just other people in the same boat. Maybe they've just done the interview you're about to do. So that can give you a lot of support and give you a community. Anyway, thanks. Hope this video was helpful. If you liked it, smash the like button, subscribe for more content. And if you have any questions, any thoughts, feel free to leave a comment.